Liquid state and liquid crystal is the chapter we are going to study. My name is Sonika. My roll number is 1221271090030. I am a student of BSc Chemistry Honors first year. Introduction. In a solid, the constant particle, atoms, ions, or molecules are closely packed, hence, they possess rigidity and have a definite volume and a definite shape. In gases, the molecules are completely free to move about. Therefore, they have neither a definite shape nor a definite volume. They fill up the vessels of any volume, also take the shape of that vessel. However, in a liquid, the molecules are not fixed as in a solid. At the same time, they have freedom of motion. Though they are not as free to move in case of gases, they show a behavior in between the gases and that of solid. Like solid, they have definite volume, whereas unlike solids, but like gases, they do not have a definite shape. They take up the shape of the vessel in which they are put. This is expressed by saying that liquid state is an intermediate between the gaseous state and solid state. As explained above, the difference in the behavior of the three states of matter is mainly due to the intermolecular distance of separation. In a solid, the constant particles are closely packed, almost touching each other, and may be treated as a hard sphere. In a liquid, the molecules are separated by small distances, the order of molecular diameter, while in a gas, the intermolecular distances are large. The molecules can move randomly within the vessel. The arrangement of particles of the three states of matter in two-dimensional space may be represented as follows. These intermolecular distances suggest that the cohesive force intermolecular force of attraction in solid are strong, whereas in case of gases, they are weak. In case of solid, they are in between. They are fairly strong to keep them in the condensed state, but not strong enough to hold them in fixed position. In fact, all the characteristics of liquids such as vapor pressure, surface tension, viscosity, etc. arise due to the nature of intermolecular forces existing in the liquids. Intermolecular forces or van der Waals force. The force of attraction existing among the molecules of substance, gases, liquid, or solid are called intermolecular forces or cohesive forces. These forces are of different types as explained below. First is dipole-dipole attraction. The force of attraction occurs among the polar molecule. Polar molecules have permanent dipole. Negative dipole of one molecule is attracted by the negative pole of another molecule. Example HCl, in which the chlorine is being more negative acquires a slight negative charge, whereas the hydrogen becomes slight positive charge. The dipole-dipole attraction takes place among the HCl molecule. Proof for the existence of dipole-dipole forces. If dipole-dipole forces exist among polar molecules, they should have higher melting point and boiling point than the known polar molecule provided all the factors like molecular mass, molecular shape, etc. are the same. This is actually found to be so. For example, the known polar molecule N2 and O2 have boiling point minus 190 degree, 6 degrees Celsius and minus 183 degrees Celsius respectively, whereas NO, which is slightly polar, has a boiling point minus 151 degree. Magnitude of dipole-dipole forces. As the charges at the end of the polar molecules are great as the charge of the ions in an ionic compound, the magnitude of dipole-dipole forces is much smaller in comparison to ion-ion attraction or ion-dipole attraction. Further, the force of attraction between the two ions is inversely square to 1 upon r square. The force of attraction between the two dipole is directly proportional to 1 upon r square. Since the intermolecular forces are very large, the dipole-dipole force of attraction among the gaseous molecules are very small. The pressure is increased or the temperature is decreased. The distance among the molecules come closer, and the intermolecular force of attraction increases, and they change into a solid or liquid. Hydrogen bonding is a special case of dipole-dipole attraction. It occurs in molecules where hydrogen atom is linked by a covalent bond to a electronegative atom, but smaller in size, Because of the large electronegative differences between hydrogen and the more electronegative atom, hydrogen acquires slight positive charge and electronegative atom acquires slight negative charge. Hydrogen bond may be defined as the attraction of hydrogen atom of one molecule by the electronegative atom of the another molecule. In case of compound containing hydrogen atom linked to highly electronegative atom. Strength of hydrogen bond. Hydrogen bond is stronger than ordinary dipole-dipole attraction. It is much weaker than the covalent bond. The energy of hydrogen bond lies between 20 to 40 kJ per mole, whereas that of the covalent bond is usually between 160 to 600 kJ per mole. Depending upon the electronegativity of the atom, the strength of hydrogen are as follows. Dipole-dipole induced Dipole-induced dipole attraction. The positive end of a polar molecule may attract the electron cloud of a non-polar molecule, which is lying close to it, thereby polarizing it. The non-polar molecule becomes an induced dipole, just as it happens in case an iron piece is brought close to a magnet. As a result, the attraction takes place between the polar molecule, permanent dipole, and the non-polar molecule, induced dipole. Now the third is induced dipole attraction, which is also known as London forces or dispersive forces. The force of attraction between the induced momentary dipoles are called London dispersion forces. London forces also exist in polar molecules. However, in case of non-polar substances, London forces are the most stronger intermolecular forces that exist. London forces are called weakest intermolecular forces. Magnitude of London forces depends upon the following two factors. First is the complexity of the molecule. Large or more complex the molecule, greater the magnitude of London forces. This is obviously due to the fact that large electron clouds are distorted. Since the large molecular size amount to large molecular mass, it often suggested that magnitude of London forces increases with the increasing molar mass. Second, geometry of the molecule. The shape of the molecule has a significant effect on the magnitude of London forces. For example, N-pentane and neopentane have the same molecular mass formula C5H12, yet the boiling point of N-pentane is about 27 degrees Celsius higher than that of neopentane. The difference can be attributed to different shape of the molecule. N-pentane being a zigzag chain and whereas neopentane is nearly spherical. The overall attraction between the molecules is greater than that of N-pentane because there are more sites of interaction. The molecules are able to come in contact with the entire length of a molecule. London forces are referred to as van der Waals force. It is interesting to mention that based on the nature of intermolecular forces, liquid are classified into the following type. First is ionic liquid, such as molten salts. Second is metallic liquid consisting of ions and mobile electrons. Third is liquid such as water in which the molecules are held together mainly by a hydrogen bond. Fourth is molecular liquid in which the molecules are held together by van der Waals forces which include interaction between permanent dipole and induced dipole. Induced dipole and induced dipole, that is London forces or dispersion forces. Now, what are the structure of liquid? To study the structure of liquid means to find out how consistent the particles are arranged within the liquid. To the following different studies help us to know about the structure of liquid, that is volume changes on fusion and vaporization. When a pure solid melts, the increase in volume is only about 1% of which is smaller than increase in volume which take place when the liquid changes into vapor at the boiling point, which is about 100 to 1000 times. Knowing that in a solid the constant particles are arranged in a perfect order, the small increase in volume or melting shows that some disorder has been introduced, but the large change in volume from liquid to vapor state reveals that the disorder from liquid to gaseous state is very large. Hence, we conclude that the constant particles of a liquid are not as ordered as that in a solid, but at the same time they are not dissolved as that in gas. Second is enthalpy of fusion and vaporization. The amount of heat which is required to melt 1 mole of a pure solid at the melting point is called molar enthalpy of fusion, which is found to be much smaller than the amount of heat which is required to convert 1 mole of the liquid obtained into vapor at the boiling point, which is called enthalpy of vaporization. Now we will study about the theories of liquid crystal. First theory is the vacancy or hole theory. That is, this theory was put forward by Ehring and Rey. The theory is based on the fact that the liquids are generally less dense than the corresponding solid. This implies that the intermolecular space in a solid is more than that in a solid. Airing and Rip, the important view that in a liquid, the intermolecular space was not random but comprised of the vacancies of the size of molecular diameter. Thus, a liquid can be considered to be consist of liquid molecules and the holes randomly distributed between them. Due to the presence of the holes, the neighboring molecules can easily jump into them and show gas-like behavior. These molecules which do not have hole in the neighborhood cannot jump and hence to show solid-like behavior. Using appropriate mathematical treatment, the mole fraction of gas and solid-like molecules can be calculated. From these values, the thermodynamic properties of the liquid can be calculated. The result thus obtained for argon by adding and Rey were found to be in close agreement with the experimental values. Second is the free volume theory. According to this theory, it is believed that the molecule in a liquid is surrounded by 10 to 12 neighboring molecules only a small distance away from the molecule. These surrounding molecules thus form a cage or a cell around the center molecule as shown. Thus, the center molecule has to move only through a small distance to collide with any of its neighboring molecule, unlike in a gas where the molecule has to travel a long distance before colliding with another molecule. The center of the caged molecule can move within the space shown by the shaded area. The volume thus available to the molecule within which the center can move is called free volume. Free volume can be calculated and can be related to various thermodynamic properties of the liquid. Now, structural differences between solid, liquid, and gas. Solid. The X-ray diffraction pattern have well-defined maxima. The constant particles are arranged in perfect order, that is, there is a short range as well as long range order. The constant particles are very closely packed, hence they have a strong intermolecular force of attraction, hence just rigidity and a definite volume. The constant particles have no translation or rotational motion, however, they have vibration motion. Solids have high density. Liquid, the X-ray diffraction pattern have only one or two well-defined maxima, which damped out with distance. There exists a short range order, but there is a long range order. The molecules are separated by a small distance, though the force of attraction are weaker than solid, but sufficient enough to hold together. They possess fluidity and have a definite volume, but no definite shape. Their molecules have translation, rotational, and vibrational motion. Density of liquid is lower than that of solid, but higher than that of gases. Gases, their electron diffraction pattern do not have any maxima. There is neither short range or long range order, rather there is a chaos of molecules. These molecules are separated by a large distance, hence the intermolecular forces of attraction are weak. As a result, they have neither definite shape nor definite volume. Their molecules have large translation, rotational, and vibrational motion. Gases have low density. Now, what is vapor pressure? Vapor pressure of a liquid at any temperature may be defined as the pressure which is exerted by the vapor present above the liquid in equilibrium with the liquid at that temperature. Cooling caused by evaporation. When a liquid evaporates, the more energetic the liquid. As a result, the average kinetic energy of the remaining liquid decreases as the temperature falls. Factors which is affecting the vapor pressure. Two important factors on which the vapor pressure of a liquid depends upon. First is nature of liquid. If the intermolecular force of attraction in the liquid are weak, the molecules can easily leave the liquid and come into the vapor phase and hence the vapor pressure is higher. The vapor pressure of either acetone, benzene, etc. is higher than that of water at the same temperature. Effect of temperature. As the temperature of a liquid is increased, the number of molecules with higher kinetic energy increases, hence the vapor pressure of the liquid increases. The effect of temperature on vapor pressure can be studied quantitatively with the help of Clashes and Clapeyron equation. Now liquid crystal. a large number of organic compounds with long chain molecule. For example, cholesterol acetate, cholesterol benzoate, para-azoxyanisole, para-azoxypentanol, ammonium algate, unknown which on heating melts sharply to give a milk turbid liquid, which on further heating becomes clear again at definite temperature. The former temperature is called transition point, where the later is called melting point. For example, para-azoxyanisole, the transition point is 389 Kelvin and melting point is 408 Kelvin. On cooling, the clear liquid melt. The reverse change takes place exactly at the same temperature. The turbid liquid thus obtained are found to be anisotropic, a property which is possessed by crystalline substances, according to which the properties like refractive index, electrical conductivity, etc., are found to be different in different directions. Hence, these turbid liquids are called liquid crystal. However, it is found that the molecules of a liquid crystal do not have the arrangement like that of a crystal lattice. Moreover, except for a few properties like refraction, etc., they behave like true liquid. They possess surface tension, they have the property of flow. Hence, in place of liquid crystal, certain other names have been proposed, such as anisotropic liquid or paracrystal. The best name for the substance, the state is mesomorphic state, which in Greek means intermediate state. In spite of all this, the original name, liquid crystal, is still frequently used. Now, type of liquid crystal. On the basis of the molecular arrangement, the liquid crystal are classified into the following types. First is nematic liquid crystal. In these crystals, the molecules are lined up in such a way that their long axes are parallel to each other, but the molecules are not arranged in layers. The parallel molecules can slide past each other. The name nematic comes from the Greek word meaning thread, as they appear thread-like when seen under a microscope. These crystals are translucent, less turbid and quite mobile, can flow. Further, they scatter light strongly. Second is matic liquid crystal. In these crystals, molecules not only have the long axes parallel to each other but also arranged in layers. These parallel molecules can slip past each other. The name sematic has been derived from the Greek word meaning these crystals are like soap in touch and structure. These crystals are more turbid, viscous than the nematic liquid crystal. Further, asematic substances transform into a nematic substance during the course of heating at high temperature. Now, third is cholesteric liquid crystal. In these crystals, the arrangement of molecules is similar to that of nematic liquid crystal. However, in these crystals, the orientation of the axis shifts in a regular way in going from one layer to the next, thereby giving a helical structure. Because of their structure, cholesteric crystals have the remarkable optical property of reflecting light of different colors under different conditions at different temperature. Based upon these properties, cholesteric liquid crystals are available which change color with person's mood with any skin temperature. The name cholesteric has been given to these crystals because these substances are all derivatives of cholesterol, but not cholesterol itself. What are the uses of liquid crystal? Liquid crystal are used in wristwatches and other electronic instrument in which digital display of black numbers take place against silvery background. Thin films of cholesteric liquid crystal are used to map skin temperature as an aid in the diagnosis of the diseased tissue and in the rings to study person's mood as already explained. Now, let's study about the thermography. Thermography is a technique of recording the temperature variation, especially of the skin or graph. The record thus obtained is called thermograph. It is based upon the fact that because of the helical structure of cholesteric liquid crystal, they have the remarkable optical property of reflecting light of different colors under different temperature. This is because the helical structure has a characteristic pitch length. These pitch lengths are in the range of wavelength of visible light. The pitch length changes on changing the temperature, but the chemical structure of the helix remain unaffected. The properties of different liquid crystal are described in terms of event temperature and clearing point temperature. The lowest temperature where liquid crystals scatter visible light is called the event temperature. At a temperature below this temperature, the liquid crystal will be in the solid state and will appear transparent. The temperature above which it becomes pure liquid is called the clearing point temperature. Depending upon the requirement, the suitable liquid crystals selected which reflect lights of different color in the desired temperature range. The most important application of thermography has been in the medical field, in especially in the early detection of diagnosis of tumor, breast cancer, beside orthopedic disease such as arthritis and back pain. The basic principle is that heat changes produced in the different parts of the skin are different from the health of healthy skin. Earlier, the physician used to paint the liquid crystal on the portions of the body to be examined, but this method was too rough. Now the method is simple. Liquid crystal are pressed against the healthier part as well as the part to be examined. Then photography are taken of the resulting pattern of colors and then compared. In fact, the principle of thermology has been used since early times. Ancient Greek physicians employed the method of thermology. They used to apply a thin mud slurry on the areas of their patient and observe the pattern of drying, thereby determining the abnormal distribution of body technique, and it is also called medical thermology. Liquid crystal display, which is also short form known as LCD, and seven segment cells. And one of the most important application of liquid crystal, somatic and pneumatic, has been in the electronic industry. They are being used in the thin weight display devices such as digital watch, pocket calculator, similar instrument. As this is done with the help of liquid crystal, the basic principle are as follows. A thin film of liquid crystal not more than 1,000th of an inch thick is placed between the two sheets of glass, one of which is coated on one side with a thin layer of electrical conductive material, such as tin oxide. When no current is passing through the conductive coating, the molecules are uniformly oriented and the light can pass through the cell. When the current is applied, the molecular alignment changes because the liquid crystal molecules are polar and the cell appears opaque or black. A number or letters display in black against silvery background. As liquid crystal requires a very small current, it consumes very little power. Electronic watches, calculator run for years with small battery. Most of the display in LED, LCD watches and calculator were composed of several 7 segment section display. Each 7 segment section can display one number, and the combination of this section display the number. Similarly, for alphanumeric display, there are 14 segment, a segment which means active area for the display. Thank you.